A practical example of using derivatives and integrals is understanding how functions behave. So we can use derivatives to actually graph what functions look like by hand. So if we were to ask you to graph f of x equals the square root of 1 minus x minus 1 squared plus 1, it might be a little confusing to graph that fully by hand. Even just looking at the properties, I know that this value means I have a vertical shift upwards by 1. And I know that this value means I have a horizontal shift to the right by 1. But how do I graph the rest of this function? What does the rest of this function look like? So I'm going to take a look at the derivative of this function and kind of figure out, what does the derivative tell me? So the derivative is the slope of the function at any given point, right? So it'll tell me if my function is increasing, if it's decreasing, and just how it's going to generally behave. But I want to figure out a simpler way to kind of make it so I don't have to test every single number of this function, because this function could, in theory, go on forever. So what I'm going to do is I'm going to set the derivative equal to 0. And by setting it equal to 0, what I'm doing is I'm creating a critical value, meaning I'm going to figure out, where does it change direction? When does it go from increasing and it stop to either go back to increasing or decreasing? So this is going to give me what's called a critical value, or a peak or dip of my function, which is essentially a maximum point or a minimum point. So if I evaluate the derivative and I set it equal to 0, I find that x is equal to 1. So I have this some critical value where my function either has a maximum or minimum point at this point. So now I want to ask myself, does this function go on forever, or is it bounded by some values of x? It's natural to assume, because I haven't been given initial bounds, that functions usually go on forever. But there are some functions that don't. So some functions have what's called natural bounds. And so what I'm going to do to determine if my function has natural bounds is I'm going to take the limit of the function as x approaches positive and negative infinity. And what I find when I evaluate the limits as x goes to negative infinity and the limit as x goes to positive infinity is that I have a negative under the square root, or I get some imaginary number. Now, I don't want my function to be in the imaginary realm. What this tells me is that there is a point where my function stops being real. And I only care about, where's my function real. So this tells me I have some natural lower bound and some natural upper bound. To determine what those values exactly are, for this specific function, I only need to look at what's inside the square root, because the point where my function stops being real is the point where my square root becomes negative. So that tells me that 1 minus x minus 1 squared has to be greater than or equal to 0. Because I can have a square root of 0, that just gives me 0, which is not an imaginary number. I cannot go below 0. The moment I go below 0 is when I have an imaginary number, when my function stops being real. So I can evaluate this. That becomes negative x minus 1 squared greater than or equal to negative 1. X minus 1 is less than or equal to plus minus 1. So x is greater than or equal to 0, and x is less than or equal to 2. This is my lower bound, and this is my upper bound. I can now use these values on a number line. I will use my lower bound, my upper bound, and my critical value to determine how does my function behave in between these points. This allows me to test only two numbers to figure out how it's going to behave. So what I do is I use the derivative again to figure out, is my function going to be increasing or decreasing between 0 and 1. So I just pick any number between 0 and 1. To make it simple, let's pick 1/2. And what I find is I get a positive number. It doesn't matter what the actual value is, I just care about the sign, because if the slope is positive, then my function is increasing. And I'm going to do the same thing between 1 and 2. What I find is I get a negative number. So my function is decreasing between those intervals. Now let's use these values and get some points on the graph so we can kind of start to see what this looks like. And to get our points, I'm going to use my lower bound, my upper bound, and my critical value. And I'm going to plug them into my original function to get their corresponding y values, because these are all parts of the points on my actual graph. And what I find is for my critical value, it is now becoming a critical point at 1, 2. So that becomes my first point. I have a lower bound at 0, 1. And I have an upper bound at 2, 1. I know from using my number line that between 0 and 1 my function is increasing, and between 1 and 2 my function is decreasing. My next step is to determine how am I increasing and how am I decreasing, because I don't know that these are straight lines. I could be increasing but slowing down, which would look like this. I could be increasing but speeding up, which would look like this. I could increase and slow down and increase and speed up. I could also do the reverse. I could do the same for decreasing as well. So in order to determine that rate of increase and how that curvature is going to look, I'm going to look at the second derivative. And what the second derivative tells me is what we call concavity. Once I evaluate my second derivative, before I determine concavity, I need to figure out if I have any new critical points. What this means is I need to determine if my concavity is uniform throughout, meaning I have just one curvature or I have multiple curvatures where my curvature will change direction. And I do this the same way I found my first critical point, as now I set my second derivative equal to 0. And what happens is my x values completely cancel out. I get -1 equals 0, which is not true. What this tells me is I have no new critical points. So I can keep the same bounds as before, and it tells me that I'm only going to have uniform curvature. So now I need to determine what direction is my curvature. Just like my first derivative told me if my function was increasing or decreasing, my second derivative will tell me if my curvature is facing upwards. I will get a second derivative that is positive. And if my curvature is facing downwards, my second derivative is negative. Because I have no new critical values, I can keep the same range from 0 to 1 and 1 to 2. And just like before, I will plug in a number between those ranges into my second derivative to determine concavity. So I'm going to pick the same numbers as before. I'm going to pick 1/2, and I'm going to pick 3/2. And what I find when I compute them is that they are both negative. And I can add these corresponding to the number line. So now I can start to form what that curvature is going to look like. So between 0 and 1, I have an increasing graph, but a negative concavity. So what that's going to look like is I have an increasing slope that is slowly slowing down. Between 1 and 2, I have a decreasing graph and also negative concavity. So what's that's going to look like is I have a decreasing slope that is speeding up. Really what we get is a half circle. And we're actually done. This is the function. It's completely graphed. We've done every point on this. So we were able, using derivatives, to graph this function by hand. We can also look at further applications of this in determining what is maybe potentially the area under this curvature. If I were to compute the integral of this function between the bounds of 2 and 0, because that's where my function exists, what I'd find is that I get an area of 3.57. Now I want to show you real quick a comparison to that to the well-known area formula for a circle, pi r squared. And in this case, we're just looking at half a circle, so we're going to divide that by 2. My current given radius for this circle is 1, because from 1 to 2 is the maximum value, and this would be my radius value. So this then becomes pi divided by 2, which is actually equal to 1.57. Why then are these numbers not the same? This integral is taking into account not only the area under the curve, but this area as well. So there's a few ways we could fix this and compute this. One of the first ways I can do is when I have initially solved for the integral, I can just leave off this plus 1. That would get me the correct area. Another way I can compute this is I can simply subtract from it the area of that rectangular shape, which is just a rectangle that is 1 by 2. So I would subtract from 3.57, I would subtract 2, and I get 1.57, which is exactly the number I get using the formula for a circle. And these numbers should be identical. They shouldn't be sort of identical unless there's a rounding error, because it's not an approximation. It gives us an exact value, because integration is just that. It's that accurate. I want you to now look at, if we're using the free online form of GeoGebra, what happens if we rotate or revolve this function over an area point. Because another application of what we can do with shapes or functions is we can create three-dimensional shapes. So this is the function just kind of graphed in here. And if I look at it like this is the y, the green is the y-axis, the red is the x-axis. I can see that I have my semicircle. Now I removed the plus 1 just because for the sake of using GeoGebra, I'm just going to revolve this around the x-axis, and the computation is easy. But the area, the surface area, the volume, any numbers I would compute from this would be the same, because that plus 1 isn't going to affect the size of that circle I'm going to create. I'm going to now create a slider, and I'm going to change its minimum value to be just above 0, and I want to revolve this into a complete circle. So I'm going to go from 0 to 2 pi, and I'm going to create a three-dimensional shape using this by using the surface function. I'm going to have the function is what I'm rotating it. I'm rotating it n equals to 2 pi, and I'm going to have that about the x-axis. What I'm going to do here is you're going to see as I go from 0, I just have the straight line. As I move this bar along, I'm actually creating a three-dimensional shape. I'm creating a sphere. And this is starting in the realm of where we can learn that we can actually find surface areas if we revolve functions and we integrate using that principle of just going around a circle, going 2 pi. We can actually find surface areas using integrals. And we can find surface areas of spheres. We can find surface areas of all sorts of shapes. For this function, it would be a sphere because we have a semicircle. And we can actually use this also to find volume, which we will look at in a later video.